So, hi everyone, this is George Magoulas. I'm professor here at Birkbeck at the Knowledge Lab, and together with my colleague Konstantinos Karoudis, we are going to give you an overview of our work on the design of interactive intelligent systems for learning and teaching. Here is the outline of my talk. So I will start by explaining our approach for designing intelligent educational software, and then I will proceed by giving an overview of the pedagogical underpinnings of our work. Then I will proceed by giving some examples of systems we developed where we have incorporated these kind of methods together with artificial intelligence techniques to design intelligent components for tools for mathematical generalization, for teachers to do learning design, and for modeling lifelong and planning lifelong learning activities. At the end, we'll give you a summary of our work. So the design of intelligent systems for learning and teaching in our approach is a kind of dialogue between education and computer science. Education has gives teaching theories, learning theories, examples of teaching practice, has a very good understanding of learner needs and of learning analytics. At the same time, computer science provides a different set of tools, artificial intelligence methods, data-driven design, computational modeling techniques, knowledge representation, and data analytics. This continuous dialogue between education and computer science gives more clarity on understanding the educational constructs behind practice of teaching and learning, and also produces new forms for modeling, greater adoption of educational tools, and achieves a better match to teachers' practice. In terms of software engineering, the projects I'm going to describe followed a more or less traditional iterative software development cycle. However, in our approach, there is strong user participation. There is a user-centered design with participatory sessions where users can give input. User data of different types are collected either through interviews or observations, but also through monitoring of interactions of users with prototype tools we are developing. And this information is processed and used to improve our design, conduct evaluation, and also collected after deployment of the tools to provide enhancements and improve the whole form of interaction and the learning experience. So the whole design approach is informed by user behavior, and in the rest of my talk I will going to explain and give some examples of how we monitor user behavior and how we use this kind of information. In terms of pedagogy, as I said, all our work is based on a strong dialogue with educational experts. Most of the tools that I'm going to present today are based on a pedagogical approach which is called Constructionist, proposed by Papert in 1993, and he also suggested a term for the use of this kind of environments. He calls these environments microworlds. So what we are doing is in reality developing intelligent microworlds where the user interaction is monitored by AI methods, and users are able to get support depending on the context of the interaction. The whole idea of constructionist learning is that learners gradually construct mental models of the world around them, and this is also transferred to the particular kind of context they study. So gradually they build knowledge structures and engage with different kind of models, constructions they develop. There are different kinds of environments that fit into this category. For example, there are virtual science labs, educational games, simulators like flight simulators. They all allow users to interact in different ways with the system. They engage learners into different kinds of learning activities and enable deep learning. At the same time, Of course, as I'm going to explain later, there are also several challenges that we need to deal with when it comes to the use of artificial intelligence methods and AI in education in general in this kind of context. But first, let me introduce you the main characteristics at a conceptual level of these intelligent microworlds. So in all of these tools that I'm going to present, there is a set of objects that users use to interact with the environment, and the objects represent some kind of concepts or models behind the knowledge domain. There are different forms of representation, so in reality there are multiple ways where users can interact with these kind of concepts and with the properties of the models and the objects. Users are able to combine different kind of objects and perform complex operations in order to accomplish different kind of tasks. And always there is a set of activities or challenges that learners are engaged. So they have to solve different problems, they need to reach different goals, and they do that in their own way using the tools that the systems provide. This freedom of interaction, although beneficial because it leads to enhanced learning and deep learning, generates complex user behavior. So the user behavior is users explore the space, they interact with ill-defined tasks and ill-defined domains, they build tools, they build different kind of models, and they are free to test their own and develop and test their own ways of thinking, as we say. They reflect on their mistakes, they make corrections, they experiment with the tools, the objects that the environment provide. As I said, the positive aspect is the high level of engagement and better opportunities to learn from our own mistakes. The challenges when it comes to modeling user behavior are several in this case. The tasks most of the time are open-ended. Users sometimes they exhibit off-task behavior. They do what we call game the system. When it's about tools for kids, educational software for kids, then they try to game the system, they try to understand how the system works and then use this kind of understanding to gain extra points or awards. So the AI methods must be careful to identify this kind of situations. There is sometimes lack of focus on task as users interact for a long time, for long periods of time with the software. Sometimes they lack focus. All the time we have to be able to find the balance between freedom of for the user and guidance, provide some kind of form of guidance so that they stay on task and we help them to accomplish their goals. An important parameter is that there are no right or wrong answers. So in contrast to other kinds of educational software where there is very specific structure, students, users need to go through some kind of tests or quizzes, here it doesn't work like that. There are many different approaches to produce a valid solution, which makes the whole issue of modeling, of interactive behavior and of assessing the models and the knowledge of the user quite challenging. So what is the role of AI tools in this kind of context? I'm going to talk about different kinds of intelligent components we have developed. These have been integrated into learning environments. The main aim, because of the exploratory nature of the software, is to support the users as they work on the different kinds of tasks. This helps them to be more productive and achieve the learning goals. Other types of uses for AI tools is feedback generation. So AI methods detect important indicators of user performance or of skills relate to some kind of competencies that users have, and they make estimations of the current status of user knowledge in order to provide appropriate kind of feedback. In another tool that I'm going to show you, which is about teachers, the aim is to monitor how teachers understand how teachers perform learning design and use this kind of knowledge to inform better learning designs. The importance of learning design has been acknowledged by different kinds of studies, and it's one of the main factors that leads to student engagement. So sharing good practice in learning design is a very important factor. So I'm going to start by giving a quick overview of one of the tools we developed in the context of the MyGen project. It's a tool for learning mathematical generalization. I'm going to focus on a particular component of this tool. It's a complex tool. It includes several components. So I'm going to talk just about one of them. It's called Expressor. It's an intelligent microworld which is used in classrooms. The audience of this tool is 11 to 14 years old. They have to work individually, so they do different kind of tasks with user support, and there is also a collaborative dimension where students are organized in groups. The system recommends, identifies skill sets in the different users and produces groups for the users to collaborate. At this point, maybe it's important to mention that this is a collaboration with people from the UCL Institute of Education, Richard Noss, Celia Hoyles, and Manolis Mavrikis. These played an important role as they provided educational expertise to help us understand better the problem and how users behave in these kind of situations, what kind of problems they have understanding mathematical generalization. I have, perhaps it's best to start with a demo, a short demo, 5-minute video that will show you how this system can be used by a normal user, and then I will go to explain one of the components that support intelligence in the system.
These are various activities students can do in Expressor. Some provide intelligent support and are designed primarily for classroom use. For this tutorial, we will choose the activity Build Your Own Model with no help. Let's open it. Adjust the construction area and the windows as you like. You can place tiles onto the construction area by clicking on a tile generator, then dragging and dropping the tiles where you like. Let's build a flower like this. Then you can group tiles to make a building block. Click on the highlighted tiles and select Make a Building Block. Now you can make a pattern. Type numbers in the number generator and drag and drop them to replace the question marks. Then choose how many repetitions of the building block you want and replace the last question mark. Notice that what you do in the construction area is mirrored in the general model. Your pattern is not colored. This is because you have not answered the question, how many tiles? There are 5 yellow tiles, 20 red tiles, and 25 green ones. Let's animate your model. To do this, you need to unlock a number. Let's unlock the number of repetitions of your building block. Expressor chooses a random value for the unlocked number in the general model. So in this case, it does not have the same number of repetitions of the building block as your model does. Let's try animating now. Oh no, your model does not remain colored. It messes up. To avoid this, you need to build expressions that always give the correct total number of tiles. The yellow tiles are always as many as the number of repetitions. So you can replace your previous answer. You can check to see that the yellow tiles remain colored now. You can change unlocked numbers manually or by animating your model. Now let's build expressions for the other numbers of tiles. You can open the Building Block Properties window. You can build expressions in the construction area using numbers from your building block properties and from your patterns properties. And then replacing your previous answers. Let's check the expression for the green tiles. It worked! You can also build expressions right in the Pattern Properties window. Notice that you can drop numbers to the left or to the right of other expressions. Now let's check that your model no longer messes up. However, the general model is still uncolored. In order to color the general model, you need to replace the question mark in the model rule area with an expression that always gives the correct total number of tiles for your model. Let's do this. You can build an expression for the model rule by using the expressions you already built. In this case, you need to add the expressions for the numbers of green, red, and yellow tiles. Let's try animating now. Hooray, it worked! You can also name numbers. Notice that in the general model, you can see the random values assigned to the unlocked number. Now you try to build a model like this one.
As you saw in the video, users are able to interact in different ways as they do different kind of tasks. The whole process is monitored by the AI components of the module, of the tool. On this slide you can see roughly how a rough schematic of the different components that lie underneath the interface. So we have the interactive environment which produces where users interact and they produce different forms of interaction. There is a component analysis module which actually consists of several units that perform different types of analysis of user traces to identify what the users are actually doing. The information of the different analysis modules is combined into the aggregation and reasoning layer. The aggregation and reasoning layer again consists of different components which combine information of the analysis module and use this kind of information to perform different types of reasoning about the feedback that the user should receive. So, for example, what type of feedback and when it should be given. The results of the reasoning module are forwarded to the third layer, the adaptive support layer. Adaptive support layer uses information, suggestions, recommendations of the reasoning module, combined this information with data stored in the user model and pedagogical knowledge to decide when is the right time to intervene and what kind of intervention scaffolding should be given to the particular kind of user. So different types of users, depending on their background, depending on the information stored in the user profiles, they're going to receive different types of feedback depending on the situation, the context of use. I cannot describe in detail the different modules. There are more than 15 intelligent components which monitor interaction and interact, and their output is combined to generate feedback. I have just an inside view of one of these components whose purpose is to identify the type of strategy, way of thinking that the users are following in order to produce one solution. So our understanding of ways of thinking is based on a detailed participatory session we did with users. So we tried prototypes, early versions of the software. We observed and identified different strategies that students use towards a particular solution. As I said, there is no one way of achieving the goal. There are perfectly valid solutions, different kinds of solutions that users should follow. Based on this analysis, we identified different categories of strategies and examples that belong to each one of them. these are used as training data to train our models. Our models have also the capability to identify new strategies that users can create. These may be similar, share some similarity with existing ones, or they may possess properties which are very important and can be added to our knowledge base of strategies. A strategy relates, in the particular case, on how users construct these kind of patterns and reflect properties and relations, attributes that these patterns have. So just to give you a quick idea, there are attributes, properties that the pattern have. There is information in the attributes about the coordinates of the particular pattern. There are different kind of labels about the color, the width, the height of the pattern, but there are also relations, and this is where the whole thing becomes more interesting, because there are temporal dependencies, value dependencies between attributes and between patterns. So a complex form of knowledge representation is generated, which is used to drive decisions of the intelligent modules. The whole problem could be formulated as a strategy identification problem, and in our approach we treat it as a similarity-based classification problem. So we use training data based on strategies, and we use similarity metrics. Our similarity metrics are mixed, so there are numeric attributes, variables, dependency relations, and we form a complex measure of similarity between patterns generated by different users, by group of users, and we identify relationships between these patterns, which are later used to identify strategies, but also to match users in order to form different kind of collaborative groups. When you develop this kind of components, of course, you have to do evaluation at different levels. So we do obviously evaluation, we validate the intelligent algorithms which are embedded in the different components, as normally we do in any kind of AI method. For example, on this slide, you can see this type of evaluation. We are trying to identify the probability of identifying a particular type of strategy based on how many components the users have used in their constructions. Obviously, if the user has just started the task and has used just one component, it's very difficult, as you can see, to identify. The probability is quite low, it's around 60%, not reliable identification. As the users progressively engage with the task and they produce more complex patterns with more components, the success of the identification, strategy identification method increases to reach a very high level. We tried, in this type of evaluation, we also validated intelligent components with comparing their decisions with experts, and calculated the agreement between the system and the recommendations of the experts. We used 4 experts. These were expert teachers teaching this kind of material in class with several years of experience, and tried to see how these people would evaluate the strategies towards the solution that the students used. In most of the time, depending on the strategy that people follow, we produce very high percentage of success for this particular component, intelligent component of the MyGen system. As you can see, there are cases where when, for example, students follow a non-systematic approach, it's extremely difficult for the system to produce reliable identification. But as you see, there is also a disagreement between the experts, as shown in the table in the data. This slide gives you different types of feedback that the system automatically generates. This can be very simple things like a suggestion box at the bottom of the page, which appears there without any particular message and waits for the user to click in case they need some kind of support. There are other type of messages that people receive depending on the context and the mistakes they make. So the system automatically will identify the problem and will give some kind of scaffolding, try to help them to correct the mistake they make. So you can see some examples here. These reflect mistakes that users at that age do, 11 years old to 14 years old, as they try to understand the concept of generalization, mathematical generalization. It's now time to progress to another, give you an overview of another project we completed. It's a completely different project. It's about learning design. It's an intelligent tool to support learning design in technology-enhanced learning. What happened is that we, again, in collaboration with our colleagues from the Institute of Education, this is a collaboration with Professor Diana Lorilad, who is an expert in learning design, we identified a serious problem which currently exists. It's this gap between theory and practice that we observe. Learning design theory is well advanced. Nevertheless, practitioners continue to learn by common practice, and the designs they produce, they are not theory informed. Sometimes they continue to use traditional form of teaching. They don't exploit, although they acknowledge the importance of technology-enhanced learning, they don't incorporate much technology in the teaching they do. So the purpose of this software was to provide a tool to support them as they design lessons, make them use technology, more advanced technology, and share experiences with other teachers or lecturers. This is an overview of the system and of the different screens it offers. There is a design organizer which shows a kind of the structure of your design. There is a main window where people can design different parts of their lesson. There is a teaching activities area where people can drag and drop already available designed activities and incorporate them in their own design. As I said, that's a collaboration with Diana Lorida from the Institute of Education, Patricia Charlton of Open University. Patricia is going to be with us today and will also participate in the discussion afterwards. At this point, it's perhaps a good idea to use another video where Diana Lorida explains the learning designer in her own words.
Hello, I'm Diana Lorillard. I'm going to describe in this video how the Learning Designer works, which is an online tool for teachers to help them prepare and develop learning design for use in either their conventional teaching or in blended teaching or in digital teaching. And part of the point of this project is to enable teachers to not only develop their own but also to import someone else's design. That's what I'm going to do here, is building from an existing session which is part of this module here called Intriguing Theories, which has three quite weird sessions in it. One's called the Altar of Pergamon, one's called Properties of Light, one's called Guess My Robot. Now these are pre-existing patterns from existing sessions which we've put together for a dummy module. But it gives you an idea of what we can do with this. The Altar of Pergamon, if we take that one, might be one that I want to try out in my own teaching, so I have a look at what it consists in. This properties page tells me it's a session which lasts for 90 minutes. It's got a design learning time of 1 hour and 30 minutes in there. The description of session, designer's reflections, students' feedback, those are all free text which tell me about the way this has been used up to now. The learning outcomes are something which I can bring in from this palette because that will tell the computer what kind of learning outcomes I've got. Now I might want to add one to that, so I can bring in this justify a position, and I can edit that into saying something like justify their position, so I can phrase it if I want to. But the computer now knows what kind of learning outcome that is. It's an evaluation outcome. So part of what we're doing here is telling the computer what our design consists in. I also want to look at what exactly are these activities, and this one at the moment consists in 5 activities which have been defined by bringing in these particular teaching learning activities from the palette over here. Each one has a particular definition to it. This is the introduction, it's a tutor presentation, there's some notes on how you can present that. What this also does is to bring up some advice and guidance on the different ways of doing a tutor presentation, or ways in which you can free up your contact time by pre-recording the student presentation. The next activity is a comparative exploration. This is a resource-based individual activity which describes what the student is doing. They then move into formulating their ideas and then move into a small group discussion. So all of these are defined teaching learning activities with particular properties which you can change. So if you think that collaborative reflection is not a combination of acquisition and discussion, but it's got some other things going on in it, for example, you might think it's got a larger amount of sorry, I haven't got the right thing open here. You might think it's got a different amount of small group discussion associated with it, so you can change the properties in the palette down here. The point of having all of this defined is that we can see that this has quite a large amount of acquisition, certain amount of discussion, certain amount of inquiry, and the analysis tab allows us to see overall what does that session look like. Now here we can see that we've got a combination of one size fits all, the black. There's quite a lot of social learning going on and a certain amount of individualized learning. Now suppose I want to increase the amount of social learning there is. So this collaborative reflection is a small group discussion, so I might want to increase that, maybe reduce one of the other things. It depends on whether I'm worried about this. Design learning time has now gone up a bit, you can see on here. So I may not be worried about that, that might be sufficient, but this will now have increased the proportion of social learning which is going on here. Probably see it more easily if I do a more dramatic increase to the amount of time. So it allows me as a teacher to sort of play with my design ideas. I can test things out, and more importantly, when I've finished it, I can then make this available to other people for them to import, and in this way create new ideas, share them with other people, but more importantly perhaps adopt other people's ideas, build on those designs and recreate someone else's design to fit what I'm doing. And in that way, if we can enable teachers to share ideas, build on each other's work, then maybe we'll get a better definition of what we know in the context of learning technologies.
So Diana Laurel gave an overview of how this system works, and now it's time to give you an overview of the intelligent methods and the approach we use to develop it. When it comes to modeling knowledge about teaching and learning design, it's a rather complex domain. There are different kinds of theories about learning design, and practitioners' understanding differs sometimes depending on the discipline. The terminology changes. There is a constant tension between theory and practice. To alleviate the situation, we had to monitor closely how practitioners perform learning design. So we analyzed tools and existing standards. We organized several workshops with users, trying to understand how they operate. We build user scenarios and storyboards that reflect different kind of situations, and try to identify the so-called, as you can see in this slide, learning design concepts. The concepts were represented in an ontology, and the process again was iterative. It took several iterations to fine-tune the concepts in collaboration with practitioners and also learning theorists in order to form a model of the domain knowledge and perform different types of evaluation. On this slide you can see a sample of the formalized knowledge, the so-called learning design ontology. There are different kinds of concepts, there are relationships between concepts, properties, like a normal ontology, and this ontology forms the knowledge, in a sense, the knowledge base of the system, the way the system understands learning design. an ontology which was informed, as I said, by educational theory, mainly based on Diana Lorillard conversational framework and practitioners' knowledge. Using this ontology, the system iteratively constructs advice, guidance, provides feedback to the user. So as users drag and drop learning activities to create learning designs, they create different kind of sessions, which includes concepts, properties, and relations represented in ontology. New learning activities that users create are also stored automatically and used by the learning design engine to make recommendations to other users about potential designs they can use. So what kind of support the system offers? The system offers different kinds of support, from traditional support, which is more user-driven, to automated support. So there are tools which allow users to browse different design, identify the structure of a design, but also a kind of recommendation engine which analyzes the designs that users produce and make recommendations about activities they can use to produce more interactive design, more user-friendly designs that will be able to engage students more in their learning. There is also a community which looks at as different designs are produced by different practitioners. Community knowledge gradually evolves, and this is also used to produce recommendations. This is how an example module looks in the Learning Designer. On the left, there is the alternative designs ideas box, where people receive different kind of recommendations. The learning experience area shows you learning analytics, learning design analytics. So the system analyzes properties of the design that the user has produced and produces this pie chart, which shows different kind of information about the amount of acquisition, discussion, inquisition, practice and production that the particular design includes. This information is used to further change the design, evolve it, make it more, enhance it with technology. You can explore the software tools I presented further. You can see the links on my slide. You can download the software and play with it. When it comes to the Learning Designer, since 2014 there is a web-based version, and you can see the slide on my the link on my slides, and also the link to the international community of users of Learning Designer, and where they have produced also different kind of learning design challenges. It would be interesting to have a look and play with this kind of tools and provide feedback if you like. Our work has been published in different papers, and I have in the slide some publications which are explain different aspects of the tools I briefly presented today. So it's time now to move to the last part. We're going to show you how we develop a new kind of framework about lifelong learning, modeling lifelong learners, and produce learning path designs throughout life. My colleague Konstantinos Karoudis is going to continue to give you an overview of the work we are doing in this area. Thank you.
Hi everyone, my name is Konstantinos Karoudis. I'm a researcher at the Birkbeck Knowledge Lab. At Birkbeck Knowledge Lab, we have developed a theoretical framework for lifelong learning modeling and learning path design. So the framework design is pedagogy-driven. That means it builds on digital learning ecosystems with built-in pedagogical affordances, and also maps the pedagogy and pedagogy continuum to learning theories and selected pedagogical frameworks. The requirement for a framework is only a single requirement, is that the learning environments must be experience API compliant. So on top of this framework, we built a system architecture which combines technological, pedagogical, and social aspects, and integrates formal, informal, and social training offerings. Our theoretical framework supports the pedagogy and pedagogy learning continuum, where lifelong learners progress in maturity and autonomy, and it can record all types of learning settings, both formal and informal, and it can record also two types of learning activities, online and offline learning activities. We have also developed a mechanism for updating the learner model. So, an important characteristic of this mechanism is that it manages efficient the learner model and the model maintenance, and uses the Experience API and distributed ledger technology. We can then use this model that we have developed to the lifelong learner model for learning path design. An important characteristic of our mechanism is the user model interoperability. So this is, of course, the exchanging of distributed user data across applications. There are three types of user model interoperability: the structural, the syntactic, and the semantic interoperability. So the last two, the syntactic and the semantic interoperability, require a high degree of alignment among applications. Current computer-based tools create separate silos of information for each learner. That means there is a reduced possibility of utilizing aggregated data over the long term. But our framework supports learning data exchange between adaptive learning systems, and this can improve the personalization services. Moreover, the application of the long-term personalization in lifelong learning may enable learners to fulfill their learning potentials. For learning path design now, there are three main sources to predict the efficient learning paths for lifelong learners. All of these three rely upon learner modeling. So these three are the course designers, sources are the course designers, the support services, and the adaptive hypermedia systems. There is also an alternative wayfinding, educational wayfinding method, which is called other learners approach. This is based on learning networks and activity nodes, on these two concepts. A learning network is a graph of nodes in a disciplinary domain, and an activity node is a learning event. In this alternative approach, there is a distinction between effective and attractive learning paths, and the logs of learner information indicate what learners did and when. These logs are used to create, of course, the learning paths. Our mechanism that implements the theoretical framework builds on the Experience API. So this is a standard developed by Advanced Distributed Learning as a means of tracking or recording learning experiences. So in the Experience API, there is always a client, which is called the learning record provider, and a server, which is called learning record store. In addition, there is a personal data logger, which stores all learning activities for a specific user. Some important characteristics of this of the API specification is that it provides a consistent format in the form of XAPI vocabulary. It guarantees semantic interoperability with the XAPI statements, and structural interoperability is achieved by exposing the API as RESTful web services. On top of that, deserialization using the JavaScript object notation ensures the syntactic interoperability. Our mechanism also uses a distributed ledger technology. This can be defined as a shared database that stores assets, either financial, legal, or physical, or maybe electronic, across multiple sites, geographies, or institutions. The security and accuracy of assets is enforced by means of cryptographic keys, signatures, and distributed consensus. Blockchain is a specific implementation of a distributed ledger and comprises a chain of data packages, which are called blocks, that hold a complete list of transaction records. A blockchain depicts a ledger of the entire transaction history, and additions to ledger are decided on a consensus basis. On this slide, we can see an example implementation of a theoretical framework. You can see that the personal data logger functionality is provided by a decentralized application. Okay. This decentralized application consists of several smart contracts. It runs on a peer-to-peer network and has its own suite, of course, of contracts. And these contracts store the Experience API statements on the Ethereum blockchain. You can see that we have two different types of accounts: the externally owned accounts and the contract accounts, which send and regulate transactions. To summarize our presentation today, we have talked about the synergistic approach that combines data-driven design, artificial intelligence, and pedagogy theory to develop intelligent components for learning modeling, learning design, and planning of lifelong learning. The intelligent components seamlessly combine explicit knowledge representation with learning and adaptation capabilities and can handle uncertainty. So that's the end of our presentation. Thank you for your attention. We're now ready to take some questions from the audience.